Let me start with something that should bother you, really bother you. Jupiter, biggest planet in the neighborhood, completes a full rotation in under 10 hours. Earth spins around once every 24. Mars, about the same. These are reasonable numbers, they make sense. And then there's Venus. Venus takes 243 Earth days to complete one single rotation. That's longer than its year. Its day is longer than its year. Let that settle in for a moment. A Venusian morning begins before the previous year has even ended. But here's the thing. That's not even the strange part. The strange part is the direction. Every other planet in this solar system, with one peculiar exception I'll come back to, spins counterclockwise when you look down from the north. The sun spins that way. The planets orbit that way. The whole system turns together like a tremendous slow carousel, all of it moving in harmony, except Venus. Venus goes the other way entirely. If you could somehow survive standing on the surface, which you absolutely cannot, because you'd be simultaneously crushed, cooked alive, and dissolved in acid, but if you could, you'd watch the sun rise in the west. Think about what that means. Something went profoundly, catastrophically wrong with that planet. And nobody, I want to be honest with you here, nobody can tell you exactly what it was. That's what I want to dig into today. Because this isn't some trivial footnote in an astronomy textbook. This is a clue about the violent, chaotic birth of the solar system. And the truth is, the case is still open. We have suspects, we have theories, we don't have a verdict. So let me walk you through the evidence and you can decide for yourself. To appreciate why Venus is so strange, you first need to understand what we should expect. Because to know something is wrong, you need a picture of right. Imagine out there in interstellar space, cold, dark, unimaginably vast. There's a cloud of gas and dust, light years across, just drifting, and now suppose gravity starts winning. The cloud begins collapsing inward, slowly at first, and then faster. Here's the key. That cloud isn't perfectly still. Some part of it, somewhere, has a tiny rotation. Maybe a passing star nudged it. Maybe a distant supernova sent a ripple through it. It doesn't matter how it started. What matters is that there's angular momentum in the system, even a whisper of it. And now, one of the most profound principles in all of physics takes over. Conservation of angular momentum says that the total rotational motion in a system stays constant as long as nothing external is applying a twist. The cloud collapses. It gets smaller. And because angular momentum must be conserved, it has to spin faster. You've watched this happen with your own eyes. An ice skater pulls her arms in toward her body, and suddenly she's spinning like crazy. She didn't push off anything. She didn't add energy. She just reduced her moment of inertia, and her angular velocity shot up to compensate. The product stays fixed. That's the law. The collapsing cloud does exactly the same thing. Contracts, accelerates, flattens into a disk. The material at the outer edge has more angular momentum and resists falling inward, so it spreads out into a wide, rotating pancake, what we call a protoplanetary disk. And everything in that disk, every grain of dust, every pebble, every growing clump of rock, but moves in the same direction, counterclockwise from the north. The sun forms at the center, spinning counterclockwise. Planets assemble from the disk, orbiting counterclockwise. As they grow by sweeping up disk material, they inherit that angular momentum and spin counterclockwise too. The whole system carries the fingerprint of that original rotation. Look at Earth spinning. Look at Jupiter. Look at Mars. They're all saying the same thing. We came from the same place, and it was turning this way. Now, this isn't just theory we made up. We can actually watch this process happening around other stars right now with our telescopes. Young stellar systems show exactly these flat rotating structures with gaps where planets are actively forming, all moving together in the same direction. The physics has been tested. Conservation of angular momentum isn't a suggestion, it's a law. So when you look at Venus spinning in the wrong direction, the first thing you should feel is deep suspicion. Because angular momentum doesn't spontaneously reverse itself. Reversing a planet's spin is like taking a flywheel, massing a billion kilograms, somehow bringing it to a halt, and then spinning it back up the other way. To accomplish that, you need a torque. And you need either a very brief, very violent one, or a very gentle one applied over an extraordinarily long time. Those are your two options. Either something hit Venus like a cosmic hammer and flipped it in moments, or something has been patiently, quietly twisting its rotation over billions of years, a violent crime or a slow conspiracy. The question is, which one? The deeper question is whether we'll ever gather enough evidence to be certain. Before we examine the suspects, let me tell you something about Venus that makes this whole affair even more maddening. We didn't discover that it spins backward until 1962. Sit with that. Venus is our nearest planetary neighbor. It's been one of the brightest objects in the sky since the first human beings looked up and wondered about it. The ancient Babylonians carefully tracked it across the sky. The ancient Greeks noticed it appeared in the morning on some days and in the evening on others, and initially assumed those were two completely different objects. They named them separately, before eventually realizing it was the same thing. Thousands of years of careful human observation, and we still couldn't tell which way it was turning. Why? Because Venus wears a disguise. It has the densest, most impenetrable atmosphere of any rocky planet in the solar system. Surface pressure is roughly 93 times Earth's atmospheric pressure. 93 times. That's comparable to being submerged about a kilometer down in the ocean. And the temperature down there sits around 465 degrees Celsius, hot enough to melt lead, hot enough to melt zinc, hotter than Mercury, despite Mercury being considerably closer to the Sun. That's the greenhouse effect operating with absolutely no restraint. 96% of Venus's atmosphere is carbon dioxide, with most of the remainder being nitrogen, and clouds made not of water droplets but of sulfuric acid drifting through the upper layers. You cannot see through that with an ordinary optical telescope. When the finest astronomers of the 17th and 18th centuries pointed their best instruments at Venus, all they got back was a brilliantly white, utterly featureless disk. Giovanni Cassini, one of the most skilled observers who ever lived, tried measuring Venus's rotation period in 1666 and 1667 and concluded it was less than a day. He was off by a factor of about 240. Other astronomers over the subsequent centuries made their own guesses. Some said 24 hours, reasoning it probably resembled Earth. Others suggested roughly 25 days. Everyone was wrong. The planet kept its secret. What broke the deadlock was radar. In the early 1960s, teams at the Jet Propulsion Laboratory bounced radio signals off Venus and measured how the frequency of the reflected signal shifted. The Doppler effect. Radar doesn't care about clouds. The radio waves punch straight through and bounce off solid rock. Here's the clever part. When you fire a radar beam at a spinning planet, the side rotating toward you reflects the signal at a slightly higher frequency, while the side rotating away returns it at a slightly lower frequency. The spread in those frequencies tells you the spin rate. The asymmetry, which side is higher frequency, tells you the direction. If the higher frequency return comes from the right, the planet spins one way. If it comes from the left, it spins the other. The radar doesn't have opinions. It doesn't carry expectations. It just measures motion. And what it found stunned everyone. Not only was Venus rotating extraordinarily slowly, 243 Earth days per rotation, it was going backward, retrograde. Richard Goldstein published the result in 1964. Some researchers initially suspected instrumental error. They were wrong. The measurements were solid. Now let me be careful about something here, because there's a subtlety that actually matters for figuring out what happened. Astronomers define a planet's north pole using what's called the right-hand rule, based on the planet's orientation relative to its orbital plane. Under that convention, Venus's rotational axis is tilted 177 degrees from vertical, nearly completely upside down, just 3 degrees away from being perfectly inverted. So you can describe the same physical situation in two different ways. You can say Venus rotates backward, or you can say Venus is essentially flipped upside down and rotates normally, but because it's inverted, its rotation appears reversed when observed from outside. Both descriptions are mathematically equivalent, but they represent different physical processes. Did something reverse the spin, or did something topple the entire planet? These would leave different traces, different evidence. That distinction matters enormously for building our case. So let's examine our suspects. Suspect number 1. The giant impact. The early solar system was not the calm, orderly place it is now. It was chaotic. It was violent. Leftover protoplanets, objects the size of Mars, or larger, were careening through the inner solar system on unstable trajectories. Collisions were commonplace. We think this is precisely how Earth acquired its moon. A Mars-sized body we've named Theia apparently slammed into the early Earth at an oblique angle about 4.5 billion years ago. The violence of that impact was so extreme that vaporized and molten rock sprayed out into orbit, and that material eventually coalesced into the moon over the span of centuries. The evidence for this scenario is compelling. The isotopic ratios in lunar samples returned by the Apollo astronauts match Earth's mantle with remarkable precision. The chemistry tells the story the way a fingerprint identifies a person. If something that dramatic could happen to Earth, why not Venus? The hypothesis is that a sufficiently massive body struck Venus, either head-on or at just the right angle, and either flipped the planet essentially upside down or slowed its rotation so dramatically that it eventually wound up going the other way. Picture a spinning top on a table. Strike it hard enough from the side and you can knock it past 90 degrees so it ends up spinning while effectively inverted, which looks like reversed rotation from the outside. Or you slow it nearly to a stop, it wobbles and topples, and begins turning the other direction. Both mechanisms are physically plausible. And notice this connects to that subtlety about axial tilt. If Venus was struck and tipped over to 177 degrees, you didn't actually reverse the spin relative to the planet's own body. You just toppled it like a gyroscope knocked past vertical. Relative to the planet itself, nothing changed. Relative to everything else in the solar system, it looks backward. There's something viscerally appealing about this theory. It's dramatic. It solves the problem in a single violent stroke. And we know from the cratering records throughout the solar system that giant impacts genuinely happened. But there are serious problems. Start with the most obvious one. Where's the evidence? When Theia hit Earth, we got the moon. Enormous, unmistakable, hanging in the sky every night, direct physical evidence of a catastrophic collision. Venus has no moon. Nothing. Not even a captured asteroid. Not a fragment of debris. If something large enough to reverse planetary spin hit Venus, where did all the ejected material go? Some researchers argue the impact was nearly head-on, so most of the energy went into heating and deforming the planet rather than flinging material into orbit. Others suggest debris was indeed ejected, but fell within the synchronous orbit radius. Here's why that matters. Because Venus rotates so slowly, the synchronous orbit, the altitude at which a moon would orbit at exactly the same rate as the planet rotates, is located very far out. Any debris disk that formed close to Venus would be inside that boundary. And material inside the synchronous orbit doesn't get pushed outward by tidal interactions the way our moon gets pushed away from Earth. Instead, it spirals inward and falls back. So any temporary moon would have been reabsorbed. There's even a hypothesis that Venus once had a moon formed from a first impact, and a second impact later destroyed it, or that the sun's tidal influence destabilized it over time. But notice what we're doing, stacking hypothesis upon hypothesis to rescue the theory. And in physics, every additional assumption is another place where the argument can fail. It should make you nervous. More troubling still, computer simulations from 2025 demonstrate that yes, a wide variety of different impact scenarios can reproduce Venus's current rotation period. Head-on, oblique, fast, slow, big impactor, small impactor. Many configurations work, and that's precisely the problem. When almost any input to your theory produces the right answer, the theory isn't really predicting anything. It's just accommodating whatever you need it to accommodate. In physics, I want to distinguish between an explanation and a description. An explanation tells you why something happened and rules out alternatives. A description merely tells you that something could have happened. The giant impact gives us a description. It doesn't give us a fingerprint. Let's consider suspect number 2. This one is slower, quieter, in many ways more elegant. It involves tides, but not ocean tides. Venus doesn't have oceans. Atmospheric tides. Here's the setup. Venus sits close enough to the sun that the sun's gravitational pull is substantial. That pull deforms the solid body of Venus slightly, stretching it into a gentle elongation along the axis connecting the planet to the sun, like squeezing a rubber ball between two fingers and watching it bulge outward on both sides. Now, if Venus is rotating even at all, this tidal bulge gets dragged slightly ahead of the Venus-Sun line by the planet's rotation and internal friction. The bulge can't keep up perfectly with the rotating planet, so it lags, and the Sun's gravity pulling on that displaced bulge applies a braking torque on the planet. It slows the rotation down. This process is gravitational tidal dissipation, and given enough time, billions of years, it's relentless. Left alone, it would eventually bring Venus toward tidal locking with the Sun, where one face permanently points sunward, similar to how Mercury has been nudged into a 3-to-2 spin-orbit resonance. But Venus is not locked. It's spinning backward. Something must be fighting the gravitational tides. That something is the atmosphere. Venus has this enormous, hot, dense atmospheric layer, and the Sun heats it unevenly. The day side gets hotter than the night side. This temperature difference creates a pressure bulge, a region of elevated pressure on the sunlit side. But the atmosphere has thermal inertia. It doesn't heat and cool instantaneously. It takes time. So this atmospheric pressure bulge doesn't sit directly at the point where the Sun is overhead. It gets displaced, shifted by the planet's rotation and the sluggish thermal response of all that dense carbon dioxide. And this displaced atmospheric bulge creates its own gravitational torque on the planet. Here's the crucial point. This atmospheric torque acts in the opposite direction from the gravitational tide on the solid body. The gravitational tides on the rock pull one way, trying to drag Venus toward tidal locking. The thermal atmospheric tides push the other way, nudging the rotation in the retrograde direction. Why retrograde specifically? Because of the geometry of how that thermal pressure bulge gets displaced, given the particular thermodynamic properties of Venus's dense superheated atmosphere. The detailed mathematics involves phase lags in the thermal response of near supercritical carbon dioxide, but the conclusion is genuinely lovely. Venus's own massive atmosphere acts as a defense mechanism against being tidally locked to the Sun. You've got a tug-of-war between two forces, two bulges, two torques. Let me give you a way to picture this. Imagine you're floating in a lazy river in a swimming pool. The current pushes you in one direction, but there's a crosswind blowing across the water surface, pushing you the opposite way. If the current dominates, you drift downstream. If the wind dominates, you go the other way. But if they're nearly matched, you barely move at all, or you drift very slowly in whichever direction has the slight edge. That's the situation on Venus. The gravitational body tide is the current. The thermal atmospheric tide is the crosswind. Venus has found the point where they very nearly balance, and the residual, the leftover net torque, is a slow drift in the retrograde direction. And remarkably, this system can reach a stable equilibrium. Not tidal locking, but a different kind of equilibrium, one where the planet rotates slowly backward. This idea was originally proposed in 1969 by Thomas Gold and Stephen Soter, and then worked out with full mathematical rigor by Alexandre Correa and Jacques Lascar starting in 2001. What Correa and Lascar showed is that when you properly account for the gravitational body tides, the thermal atmospheric tides, and the dissipation at the boundary between Venus's mantle and core, the planet's spin evolves from almost any starting condition into one of exactly 4 possible end states. Picture a marble rolling across a landscape with 4 valleys. No matter where you release the marble, it eventually rolls into one of those 4 low points. 2 of the valleys correspond to prograde rotation with a period around 77 days. 2 correspond to retrograde rotation with a period around 243 days. The retrograde valleys are deeper, more stable. Venus appears to have settled into one of the retrograde valleys. No catastrophic collision required. Just the patient, billion-year work of the Sun's gravity pulling on Venus's body and heating Venus's atmosphere, fighting each other to a standstill, and that standstill happens to be a slow, backward spin. Let me make sure you really feel how remarkable this is. It means Venus's retrograde rotation might not be an accident at all. It might be what physicists call an attractor, a natural destination. If you wound back time and gave Venus a completely different initial spin, faster or slower, tilted differently, the same forces would still steer the planet toward one of these 4 outcomes. The current state isn't a random result of some chaotic early event. It's where the physics points. The way water flows downhill, regardless of where you pour it, different paths, same destination. And the theory makes a genuinely testable prediction. Any rocky planet of similar mass at a similar orbital distance from its star, with a thick enough atmosphere, might tend to evolve toward a similar slow retrograde rotation. As we discover more rocky exoplanets orbiting close to their stars, we might find that retrograde spin is actually common, not a curiosity but a predictable outcome. That strikes me as beautiful. A catastrophic impact leaves wreckage, craters, moons, chemical scars. This tidal process is invisible, silent. It operates over geological timescales with nothing to see, just one torque quietly winning out over another across billions of years. But does the tidal theory actually work? It has one enormously appealing feature. It explains Venus's current state using forces that are acting on the planet right now, at this very moment. We're not invoking some unobservable ancient collision. We're pointing at the sun and saying you did this and you're still doing it and we can calculate it. But the theory has a real problem with initial conditions. If Venus started out spinning fast, the way most planets do, completing a rotation every few hours, the atmospheric tides may not have been powerful enough to overpower the gravitational tides within 4.5 billion years. Depending on which model of tidal dissipation you use, Venus needed a starting rotation period somewhere between roughly half a day and 3 days for the atmospheric mechanism to win in time. So what slowed Venus down in the first place? Perhaps a moderate impact, nothing like the planet-shattering collision of Suspect 1, but something substantial enough to knock the initial rotation from a few hours down to a couple of days, after which the atmospheric tides could take over and finish the job over billions of years. A hybrid scenario. The impact didn't reverse the spin, the atmosphere did that. But the impact created the initial conditions that made atmospheric reversal possible. And honestly, this might be the most accurate picture we currently have. Not one cause acting alone, but two working in sequence. A conspiracy. The impact softened Venus up, and the atmosphere delivered the slow, quiet coup de grace. It's less dramatic than a single catastrophic event. It's less mathematically clean than pure tidal evolution. But nature has absolutely no interest in being tidy for our benefit. Nature does what the forces dictate, and the forces on Venus are complicated, multiple, layered, operating on different time scales, interacting in ways that resist simple summary. That's usually how physics actually works when you look closely. Now let me tell you about something genuinely eerie that I haven't mentioned yet. Venus is still changing its rotation. We measured it carefully in the early 1990s, when NASA's Magellan spacecraft spent 4 years orbiting Venus and mapping its surface with radar. From tracking how surface features rotated beneath the spacecraft, scientists calculated a rotation period of 243.0185 Earth days, very precise. Then 16 years later, the European Space Agency's Venus Express arrived. Its infrared instruments could peer through the atmosphere at the same surface features visible to Magellan. When scientists compared the positions of those features to the Magellan maps, something was off. Surface landmarks had shifted by up to 20 kilometers from where they should have been. The planet had slowed down by about 6.5 minutes. Over 16 years, in absolute terms, that's a tiny change, but for a planet, it's astonishing. Earth's rotation changes by milliseconds per century, and most of that is the moon gradually sapping our angular momentum. Venus changed by minutes per decade. Something is actively wrestling with its spin right now. The leading suspect for these shorter-term fluctuations is the atmosphere, specifically the ferocious winds circulating through Venus's upper layers. Those winds blast along at 360 kilometers per hour, completing a full circuit of the planet in just 4 Earth days. 4 days, while the surface below takes 243. Stop and think about that ratio. The atmosphere is spinning roughly 60 times faster than the solid planet beneath it. We call this superrotation, and it is one of the most bizarre phenomena anywhere in the solar system. On Earth, atmospheric winds are driven by differential heating between the equator and poles, and our atmosphere can never outrun the surface. The ground drags the air along. On Venus, the atmosphere has somehow broken free of that constraint. It tears around the planet at extraordinary speed, while the surface barely creeps. and we don't fully understand how. The sun's heating should drive some circulation, but our models can't reproduce wind speeds anywhere near that strong. Something in the dynamics of Venus's thick, hot atmosphere creates a feedback mechanism that accelerates the winds far beyond naive expectation, and those winds matter for the rotation problem. That massive discrepancy between atmospheric speed and surface speed means constant friction at the interface, constant transfer of angular momentum between atmosphere and solid planet. When atmospheric circulation intensifies during some weather cycle, it can extract angular momentum from the surface and slow the planet's rotation. When circulation weakens, some angular momentum flows back and the rotation speeds up slightly. These atmospheric cycles on Venus might play out over decades, possibly longer. We genuinely don't know because we don't have enough data. Magellan gave us one snapshot. Venus Express gave us another. The difference between them could be a long-term trend or a single ripple in a centuries-long oscillation. Two data points cannot tell you which. Now let me tell you about a coincidence that might be nothing, but it's the kind of nothing that keeps physicists lying awake. Every time Venus swings to its closest approach to Earth, roughly every 584 days, Venus presents almost exactly the same face toward us. The same hemisphere is pointed at Earth during every close encounter. 5 Venusian solar days fit into that 584-day interval with almost frightening precision. The ratio is 5.001444. Not 5, but agonizingly close to 5. Is this a genuine physical resonance, with Earth's gravity, weak as it is across that distance, somehow nudging Venus's rotation into a precise relationship with Earth's orbital period? Or is it a numerical coincidence of the kind that inevitably shows up when you have many numbers floating around? Gold and Soter, the same researchers who proposed the atmospheric tide theory, argued it might be real. Their reasoning was this: if the two dominant torques on Venus, gravitational body tide and thermal atmospheric tide, nearly cancel each other, then the net force on Venus's spin is tiny, and when the net force is tiny, even a very small additional influence, like Earth's gravitational tug during close approaches, might be enough to tip the balance and stabilize a resonance. It's like two arm wrestlers perfectly matched, neither budging, and then a child rests one finger on one of their hands, and that's enough to decide it. More recent analysis has been skeptical, though. The current consensus leans toward coincidence. Earth's gravitational effect on Venus is simply too feeble to account for the near resonance. Probably a coincidence. Probably. But then there was a paper by Caudle in 2010 proposing something genuinely wild. Maybe the resonance isn't with the whole planet. Maybe it's only with the core. If Venus has a liquid outer core surrounding a solid inner core, with friction at the core mantle boundary, the inner core might behave somewhat independently of the mantle. The mantle rotates at one rate, pushed and pulled by the atmosphere and solar tides, while the dense iron-rich inner core deep beneath responds to gravitational forces differently and might lock into a resonance with Earth's tidal pull even while the mantle does not. The two would be decoupled, spinning at slightly different rates, exchanging angular momentum through friction at the boundary without being forced into lockstep. I find this image extraordinary. Deep inside Venus, beneath 800 kilometers of rock and a layer of liquid iron, there might be a solid iron heart rotating quietly at a rhythm set not by its own planet, but by ours. The surface is scoured by hurricane-force winds and 400-degree heat. The atmosphere is a swirling acid bath. And at the center, the core turns in patient synchrony with Earth's orbital heartbeat, a hidden clock keeping our time. Is it true? We have no idea. Testing it would require detailed measurements of Venus's internal structure, a seismometer planted on the surface, or extremely precise gravity measurements from orbit over many years. We have neither. And this is where I need to issue a warning. In planetary science, in all of science, really, there is a constant temptation to select the theory that makes the most satisfying story and promote it as the answer. The catastrophic impact is dramatic. The atmospheric tidal reversal is elegant. The Earth resonance is mysterious and tantalizing. Each one makes a good narrative. And human beings are storytelling animals. We are deeply uncomfortable with open questions. We want the detective to point at the suspect and say that one, right there, he did it. But the honest truth is we don't know what happened to Venus. All three suspects are plausible. All three are self-consistent. All three can be made compatible with the available data, but the data is sparse. We have the rotation rate, we have the direction, we have one measurement of change across 16 years. We have no samples from the surface, no seismic data, no long-term rotation monitoring, nothing equivalent to the moon rocks that confirmed the Theia hypothesis. We are trying to solve a homicide with a single footprint and no witnesses, and that's not a failure of science. It's the current state of the investigation. Any detective who tells you a case is closed when all the evidence is circumstantial is either deceiving you or deceiving themselves. The honest detective says here is what the evidence supports, here is what it doesn't, and here is precisely what I would need to make an arrest. So, what would we need? First, knowledge of Venus's interior. Is the core solid or liquid? Does it have a solid inner core? What are the density layers? This information constrains tidal dissipation models and determines whether the resonance hypothesis is even physically feasible. You could get some of this from very precise Doppler tracking of an orbiting spacecraft, measuring tiny fluctuations in Venus's gravitational field. Better still, you'd want a seismometer on the surface. But that is brutally, almost absurdly difficult. Let me tell you about the Venera program because it illustrates exactly what we're up against. The Soviet Union began sending probes to Venus in the early 1960s. The first several were destroyed by the atmosphere before reaching the surface. Engineers hadn't anticipated pressures that extreme. Nobody had. They rebuilt the probes as armored pressure vessels, sealed titanium spheres engineered to survive conditions comparable to the deep ocean. Venera 7 reached the surface in 1970 and transmitted data for 23 minutes before going silent. Venera 9 sent back the first photograph ever taken on another planet's surface, a grainy panoramic view of flat angular rocks beneath a dim, overcast sky. The light on Venus is peculiar. Despite sitting closer to the Sun than Earth, the surface is dimmer than you'd expect because those acid clouds absorb so much sunlight, and what filters through gives everything a brownish-orange cast, like the view through a dirty oven window. Venera 13 in 1982 lasted 2 hours and 7 minutes. It returned color images of flat basaltic slabs, some cracked and weathered, reaching to a hazy horizon, the edge of the lander itself visible in the frame. Then the signal stopped. 2 hours. Heat consumed the electronics. Pressure broke the seals. Sulfuric acid attacked whatever remained. Every photograph we have from Venus's surface was captured in those desperate final minutes, before our machines were destroyed. That's how close we've gotten to that planet. Second, we need long-term precision measurements of Venus's rotation rate. Not 2 snapshots 16 years apart, but decades of continuous monitoring. Is that 6.5-minute slowdown a single event, part of a long oscillation that averages out over centuries, or a sustained directional trend? You cannot answer that from 2 data points. You wouldn't diagnose a heart condition from 2 blood pressure readings taken 16 years apart. You need a continuous time series. That requires either a dedicated orbiter monitoring Venus over many years, or a network of radar stations watching it across decades. Third, and most ambitiously, we need surface samples, rocks from Venus brought back to laboratories on Earth for isotopic analysis. If a giant impact occurred, the geochemistry of Venus's crust might carry a record of it, the way lunar rocks preserve the record of Theia. If Venus once had a moon that was subsequently reabsorbed, there might be subtle isotopic anomalies in the surface material. The ratios of certain elements, tungsten isotopes, siderophile elements that preferentially migrate into planetary cores, could reveal whether foreign material was incorporated into Venus's mantle by a massive collision. But achieving sample return from Venus is orders of magnitude harder than from Mars. Surface temperature melts tin and lead. Pressure would crumple most containers. The atmosphere corrodes metal with sulfuric acid. Any mission capable of drilling into rock, sealing a sample, and launching it back through 93 atmospheres of carbon dioxide would represent engineering unlike anything we've ever attempted. We don't have the technology yet. We might within a few decades. When we do, Venus may finally tell us what happened. None of this is easy. None of it is impossible. And that's what makes Venus's backward rotation a living, breathing mystery rather than a closed historical question. New theoretical models appear every few years. New missions are being planned. The investigation continues. Let me step back and tell you what this whole thing reveals about how physics actually operates. When I was a student, the solar system was presented as a story of elegant order, angular momentum conserved, planets assembled neatly from a spinning disk, all moving in harmony like clockwork. And that picture is largely correct. But in physics, largely correct is a tremendously important phrase, because the gap between largely correct and completely correct is precisely where all the interesting science lives. Venus spinning backward. Uranus tipped so far onto its side that its axis lies nearly parallel to the plane of the solar system, its moons orbiting in the plane of its equator, perpendicular to everything else, suggesting whatever impact tilted Uranus either predated the moons or created them. Venus has no moons, no rings, nothing orbiting it whatsoever. Whatever happened to Venus left the planet stripped and alone. And then there's Neptune's moon Triton, orbiting in the wrong direction, almost certainly a captured object that wandered too close and got trapped. Mercury locked into a 3-2 spin-orbit resonance because its orbit is just eccentric enough to prevent simple tidal locking. Each of these is an exception to the clean story, and each exception is a window into something real. Some process we haven't fully worked out, some event we haven't fully characterized. If the solar system obeyed the simple story perfectly, we wouldn't learn much from studying it. The anomalies are the teachers. Every deviation is a question the universe is asking us, and the quality of our science is measured by how honestly we engage with those questions. Can we sit with uncertainty? Can we say this is interesting and I don't yet understand it without flinching? Or do we rush to an answer because the open question makes us uncomfortable? Here's something I feel strongly about. The uncertainty is the best part. It means there is still something real left to discover. When every question is answered, physics becomes bookkeeping. As long as Venus is spinning backward and we can't fully explain it, there is something genuine about planetary formation and evolution that remains to be grasped. That should excite you. The next piece of evidence, from a future mission, a new model, a lucky observation, might suddenly break the case open, and Venus itself is not misbehaving. It is following the laws of physics with complete fidelity. Every equation of motion is satisfied. Angular momentum is conserved across the whole system because the sun and the atmosphere are both applying torques, and those torques are real physical forces. The planet is doing exactly what physics says it should. The failure is entirely on our side. We haven't yet identified all the forces, all the ancient events, all the interactions that steered Venus to this particular state. Until we do, Venus's backward spin remains one of the great open puzzles in planetary science. Let me leave you with one final thought, and this one matters to me personally. Venus is frequently called Earth's twin, nearly identical mass, nearly identical size, nearly identical density, assembled from the same raw materials in the same region of the same protoplanetary disk at almost the same distance from the same star. If you knew only those facts, you'd predict two nearly identical worlds, and yet one of them has blue oceans and living forests and people having arguments about angular momentum. The other has a surface hot enough to melt lead, an ocean of carbon dioxide and sulfuric acid in the sky, and a backward rotation we cannot fully explain. Somehow, across 4.5 billion years, these two siblings diverged catastrophically. Earth went one way, Venus went another. The rotation is part of that story. A planet's spin shapes everything: its weather patterns, its magnetic field, its atmospheric circulation, how heat is distributed, how it responds to tidal forces. A slowly rotating planet with a massive atmosphere behaves completely differently from a rapidly spinning one. A planet where the sun rises in the west has a Coriolis effect running in reverse. The rotation of Venus isn't decorative. It's a piece of the puzzle of why Venus became a furnace while Earth remained a garden. Understanding what happened to Venus's spin might help us understand the whole divergence, and understanding the divergence might tell us something profound about what makes a planet capable of harboring life. That's why this question reaches beyond astronomy. It touches on what makes our own world possible, on how thin the margin is between a place where life flourishes and a place where lead puddles in the afternoon. Science gets communicated in ways that are more certain than they should be. People want answers. They want the mystery resolved with a ribbon on it. They want the detective to make the arrest. And sometimes that's justified. Sometimes the evidence really is overwhelming and the case genuinely is closed. But sometimes the evidence just isn't there yet. And the honest thing to say is, we don't know. That willingness to say I don't know is not weakness. It is the bedrock of honest inquiry. The moment you pretend to more certainty than you have, you stop looking, you stop questioning, you stop doing science. Venus teaches patience. It concealed its rotation for 3 centuries. It hid its surface behind sulfuric acid clouds. It destroyed every machine we sent down to investigate it. And it's still changing, still evolving, still keeping secrets. That's not frustrating. That's wonderful. That's exactly what a good mystery should do. Resist easy resolution and reward the people stubborn enough to keep asking. Venus has been rotating slowly backward for billions of years. It can wait a little longer for us to understand why. So here's what I'd like you to think about as you go. If you had to lay your bet, if you had to name the culprit, which would it be? The ancient catastrophic impact? The slow, patient reversal driven by the tug of war between solar gravity and the planet's own atmosphere? The subtle resonance with Earth, perhaps hidden inside Venus's iron heart? Or something no one has imagined yet? Because somewhere inside that question is a lesson about how the universe actually operates, which is almost always messier, more layered, and far more surprising than any single story we try to tell about it.